Welcome to the third video session of our first chapter. Today we will continue with the crystal lattice. Now when tiles are placed over the floor to cover it, a repeated pattern we can see. If after setting the tiles on floor, we mark a point at the same location in all the tiles, that is the center of the tile if you are taking, then we can see, and after that just ignore the tiles and we see the marks, how it will be like a set of points, and this set of points is the scaffolding on which the pattern has been developed by placing tiles. That means it's a structure then in which pattern the tile is arranged. This scaffolding is a space lattice on which two-dimensional pattern has been developed by placing the structural units or the tiles. The structural unit is said to be the basis or the motif. In crystal structure, motif is a molecule, atom or ion. That is, if you are taking a NaCl crystal, you are having each and every corner the Na plus ion and Cl minus ion in alternate positions. So, the Cl minus or the Na plus is acting as the motif, that is ion there. A regular three-dimensional arrangement of points in space is called crystal lattice. Now we can see the characteristics of crystal lattice. Each point in a lattice is called the lattice point or lattice site. That is, each corner we are taking it as the lattice site. Each point in a crystal lattice represents one constituent particle, which may be atom or molecule or ion. Just now we said about the example of NaCl crystal. If it is having a crystal, it might be having number of Na plus and Cl minus ions. So that is acting as the constituent particle there. Lattice points are joined by straight lines to bring out the geometry of the lattice. This one, if we are making the constant particles with lines or straight lines, you'll get a straight line in that lattice points, and we can find out which geometry the crystal possesses. Now let's see the example of a crystal. Here you can see a crystal lattice where we are having different colored balls, and each point is represented as the lattice point. Now let's see the unit cell, the smallest structure of which the crystalline solid is built by its repetition in three dimensions is called a unit cell. So when we were learning about the crystalline solid, we learned it is a regular and orderly arranged structure. So it is repeated again and again in the entire crystal. That repeated structure is said to be unit cell. So in this crystal itself, we are having a unit cell. We are having many unit cells, and this one cube is represented from this crystal. This one cube is represented as one unit cell, and you can see in this structure the number of cubes here, and this shaded part is the one unit cell. The same way you can take the next unit cell. Again the next is there. So different unit cells are present in a crystal lattice. The characteristics of unit cell, when we want to explain, first of all we have to take one cube as a unit cell, and then we know that how many corners are there for the unit cell. You can see here 1, 2, 3, 4, 5, 6, 7, and this one is 8. So 8 corners are there for the cube, and these 8 corners represents its lattice point. Now if you are taking the edge lengths as A, B and C in 3 dimensions, the angles between the edges are taken as alpha, beta and gamma. These are the dimensions with which we are explaining the unit cell. So let's see how we can characterize the unit cell. Its dimensions along the 3 edges are said to be A, B and C. Just now we have seen here, this is A, B and C. These edges may or may not be mutually perpendicular. It has variations. The second point for the characteristic is the angles between the edges, that is alpha, beta and gamma. That is alpha we have taken as the edges between B and C. This one B and C, alpha. Then B, C and A, or A and C, we have taken beta. A and B, we have taken gamma. Thus, a unit cell is characterized by 6 parameters, that is, the edges and the angles between them. A, B, C, alpha, beta, and gamma. So, these are the unit cells characterization, how we can explain in 3-dimensional structure. Now we have to learn the different types of unit cells. Unit cells can be broadly divided into 2 categories, that is, primitive and centered unit cells. So it is classified into how many cells? Primitive and centered unit cells. We can give the name to this primitive simple cube also. So let's see the first one as primitive unit cell. Now this primitive unit cell can be named as simple cube also. And how we can represent or define it is when constituent particles are present only on the corner positions of a unit cell, it is called a primitive unit cell. When constituent particles are present only on the corner positions of a unit cell, it is called a primitive unit cell or simple cube. So see this cube. This cube is taken and we know that 8 corners are there for this cube. 1, 2, 3, 4, 5, 6, 7 and 8. These 8 corners, only the constituent particles are there. Then we can name it as simple cube or primitive unit cell. A simple cell. Next one is about the centered unit cell. Centered unit cell, how we can define is when a unit cell contains one or more constituent particles present at positions other than corners in addition to those at the corners. It is called a centered unit cell. That means a simple cube will be there. So it is having already what? The 8 corners, 8 constituent particles. But other than this, the places are there or the positions are there where the constituent particles are there. So if more than these 8 corners the constituent particles are present in the cube or unit cell, then we can name it as centered unit cell. So along with these 8 corners, the constituent particles are present at different positions and we can classify them into 3. So centered unit cells are classified as 3 types. And the first one is body centered unit cell. With the name itself, we can understand that body means the cubes or the simple cube's body. Center part, what will be there? A constituent particle is present along with the 8 corners. Then we can name it as body centered unit cell. And how we can define is such a unit cell contains one constituent particle, that is, it can be atom, molecule, or ion, at its body center, besides the ones that are at its corners. Now, you can see in this diagram, first the red spots or red balls, which represents the simple cube, that is, 8 corners, 8 constituent particles are there. Along with that, the cube center part is it, the body, right? This yellow particle. This is present at the center of the cube, that is body of the cube. Only one particle is there extra compared to the simple cube. Then we can name it as body centered cell or BCC. The next one is face centered unit cell. So we can give the small short form for this one, FCC. Now here face centered, with the name we should know that the cube should be having faces or cube is having faces. So along with the 8 corners, all the faces, if the particles are present, then we can name it as face centered unit cell. So how we can define is such a unit cell contains one constituent particles present at the center of each face besides the one that are at its corners. That means the 8 corners are there in the face centered cell, that is simple cube, plus we can see here 6 faces of a cube. The first face, on the first face you are having the center part of constituent particle. Second face you are having second one. third phase, fourth phase, the other side of the this is a 3 dimensions, so you have to make it like this point only. So total how many faces are there for the cube? 6. And all the 6 faces, if the constant particles are present along with the 8 corners of the simple cube, then we can name it as face centered unit cell or FCC. Now the last one is end centered unit cell. In such a unit cell, one constant particle is present at the center of any two opposite faces besides the one present at its corner. So all the 8 corners are there. You can see here all the 8 corners are there. The constant particle. So it is a simple cube. But along with that, what should be there? The two faces which are opposite to each other. Here we are having 6 faces. So we will get what? 3 pairs of faces. Among the pairs of faces, any one opposite face you have to take. So if in this example I have taken the up and the down faces of the cube, then we have to take it as this one as opposite. We can name it as end face cell or end face centered cell. Now, if I am taking this side part, this face, the opposite of this one will be this one. So we don't want these 2 points there that time. So only one opposite face we are having the constant particles along with the corner of the corner of the cube, simple cube, the constant particles. Then we can name it as end face centered cell. So these are the 3 classifications of centered unit cell. So first one is what? The unit cell is divided into 2. That is primitive and centered unit cell. Primitive means it's a simple cube where we are having the constant particles at all the 8 corners. That is said to be primitive. If we are talking about the centered means along with the 8 corners of a cube, we will be having in different positions the constant particles. And we are classifying it as 3. Face centered, body centered and end centered. If it is body centered, along with the 8 corners, the center of the cube will be having one constant particle. Face centered, along with the 8 corners of the cube, we will be having 6 faces, the constant particles. And if it is end centered unit cell, we will be having 8 corners plus the 2 opposite faces. Any one of the 2 opposite faces, you will be having the constant particles. So these are the classifications. Next is the primitive unit cells are classified as 7. That is 7 primitive unit cells we have. The first one is cubic unit cell, second triclinic, third monoclinic, fourth orthorhombic, fifth tetragonal, sixth hexagonal, seventh rhombohedral, or the other name of that one is trigonal. So these are the 7 primitive unit cells. That means these structures will be having only the 8 corners where we are having the constant particles, and the structure of these primitive cells are here, where we are having the different edge lengths and the different interfacial angles. Now this one is what? Cubic unit cell. Tetrahedral, tetragonal we can name, or tetrahedral we can give. Then orthorhombic, monoclinic, hexagonal, rhombohedral, or and the last one is triclinic. So these are the 7 primitive unit cells, and we can remember the name with a short form, that is cute mother. Just remember this one, CUT, cute. Then MOTHR. E is not there, but still you can just remember these words so that it will be very, very easy to remember the 7 primitive unit cells. Cute mother, CUQ, cubic. Then T represents triclinic, M monoclinic, mother MO, O represents orthorhombic, T again T is the tetragonal, then H hexagonal, R rhombohedral. Triangle is the other name, so you can leave this one just for your information I have given. So it's for cute mother. This way we can remember the 7 primitive unit cells. Next one is Bravais lattice. A French mathematician, Bravais, showed that there are only 14 possible three-dimensional lattices, and these are called Bravis lattices. So the name came from the scientist Bravis, and you can have here the 14 Bravis lattices of the 7 primitive unit cells. The first one is cubic, and the possible variations are: first one, it is having primitive or the simple cube is there, plus face centered and body centered. Here no end centered is there, and you can see here the axial distance, or what we name edge lengths ABC, that one is equal. All the three edges are equal, but the axial angles, when we are saying, that also are equal in this case. And the example for that one is sodium chloride zinc blend, that is zinc sulfide and copper. These crystals are having the cubic structure unit cell. The next one is tetragonal, where we are having the possible variations in primitive and body centered. And here we can see the edge length A equal to B, which is not equal to C, and alpha, beta, gamma will be equal to 90 degree. And the example is tin, stannous oxide, titanium oxide, and calcium sulfate. Next one is orthorhombic, where we are having the primitive, face-centered, body-centered, and end-centered. So in this orthorhombic, we are having the one cubic, simple cubic, and the three centered unit cells. So all the four are present in this one only. And here we can see A is not equal to B, B is not equal to C. So all the edge lengths are different, and angles, when you take, it is equal to 90 degree. So all are equal. The example for that one is aromatic sulfur, potassium nitrate, and barium sulfate. Here N is not N-A-N-D is there. The spelling mistake is there. Please correct it. Next one is monoclinic, and here it is having primitive and end-centered only. And the edge length is A not equal to B, not equal to C. So it is not equal to each other. But angles, when we take, alpha and gamma are equal to 90 degree, but beta is not equal to 90 degree. Monoclinic sulfur and sodium sulfate, which is having 10 moles of water. These are the examples for monoclinic structure. And here you have seen the two names, rhombic and monoclinic sulfur. These are the allotropes of sulfur. Next one is hexagonal crystal, where we are having only the primitive. And here A equal to B is not equal to C. But alpha and beta will be equal to 90 degree, gamma is 120 degree. And the example is given as graphite, ZnO, zinc oxide, and cadmium sulfide. The next one is rhombohedral, where we are having primitive, then A equal to B equal to C. Alpha, beta, gamma, which is not equal to 90 degree. And the example for that one is calcite and cinnabar. These two are the ores of calcium and mercury. Then next one is triclinic. It is also having the possible variation only in primitive. And the next one is what? Axial distance. A is not equal to B is not equal to C. And also the gamma, alpha, gamma, beta are not equal to 90 degree. And the example for that one is copper sulfate, hydrated one, 5 moles of water is there. Then boric acid and potassium dichromate. These are the examples for triclinic. So with this, what we can remember is all the 7 crystal primitive unit cells are there here. And it has 14 variations. And 14 variations are named as Bravis lattices. And easily you can remember hexagonal, rhombic, and triclinic are having only the primitive one. Orthorhombic is having all the 4, primitive plus face-centered, body-centered, and end-centered. Next one, what you can remember is monoclinic, primitive and end-centered. Tetragonal, primitive and body-centered. And cubic, primitive, face-centered, and body-centered. That means tetragonal, monoclinic are having 2 possible variations, and cubic is having 3. Orthorhombic is having 4. The remaining 3 are having only primitives. And one thing we can notice here, that all the 7 crystals are having the primitive variation or primitive one, that is simple cube. So these are the possible 14 variations in in the 7 primitive unit cell, and we are naming it as Gravis lattice. And thank you. We'll continue in the next session.